To show that this given function is continuous. Second, cauchy-riemann equations are satisfied at the origin. Third, yet the derivative of fz does not exist there, means the derivative of fz is not existing at the origin. So this is the given function where f of 0 is equal to 0. Let this fz is equal to u plus iota v, where u is a real part of this function. Now adjusting this numerator, we can write this as x cube minus y cube plus iota x cube plus y cube, right? And in the denominator we are having x cube plus y square. So what would be the real part? It is x cube minus y cube divided by x square plus y square. And the imaginary part is, just equate these two. So this is x cube plus y cube divided by x square plus y square. Now first we need to show that this function is continuous. Now because u and v, these are the rational functions of x and y, and rational functions of x and y with non-zero denominators, because it is given that z is non-zero, right? Z equal to x plus iota y. This is non-zero, which means their denominators are non-zero, right? Now because u and v are rational functions with non-zero denominators, so these are continuous functions of x and y. Rational functions are continuous everywhere. Since u and v are rational functions of x and y with non-zero denominator for z not equal to 0, therefore for non-zero z, u and v are continuous. U and v are continuous for non-zero z. Let's talk about the origin. Now at the origin, u and v equal to what? Because it is given that f of 0 is equal to 0, z equal to 0. That is x plus iota y is equal to 0, which simply mean that x is 0 and y is 0. So from that we can say that u is 0 and v is 0, because u and v are what? U is this and v is this. So therefore we can write u to be equal to the function x cube minus y cube divided by x square plus y square when xy is non-zero and is equal to 0 for xy to be equal to 0, right? Similarly, we can also write this for v. Now we will prove that u and v are continuous at the origin, right? Now since limit xy tending to 0, 0 on uxy is equal to, yes, limit xy tending to 0, 0, writing uxy over here, we get x cube minus y cube divided by x square plus y square. So this is equal to just separating the numerator. So writing this limit on x cube divided by x cube plus y square minus the limit on y cube divided by x cube plus y square. Can I write this as x into x square divided by x square plus y square minus the limit on similarly y into y square divided by x square plus y square, yes? Okay. Now as x square is less than equal to x square plus y square, we can also take the mod, right? If I take this to the denominator, I get mod of x square divided by mod of x square plus y square to be less than equal to 1. Yes? And the limit xy tending to 0, 0 on this x, this is equal to 0, right? So this part is less than equal to 1 and the limit on this x is 0. So this limit is coming out to be 0 minus, similarly this is also 0. So that is equal to u 0, 0. Is it okay, fine? Which is the definition for the continuity. So we write here that therefore u is continuous at the origin. And similarly we write that v is also continuous at the origin. Similarly vxy is also continuous at the origin. So we have shown that u and v are continuous at the origin and also at other points of the finite part of plane. And because f of z is u plus iota v, so f of z is also continuous everywhere in the finite part of the plane. So hence, f of z is continuous everywhere. And now moving on to the Cauchy-Riemann equations, we need to show that Cauchy-Riemann equations are satisfied at the origin. For that, finding the partial derivative of u with respect to x on 0, 0, that is for the origin. So this is limit x tending to 0, ux0 minus u0, 0 divided by x, that is equal to limit x tending to 0. Okay, what is ux0? U is what? U is x cube minus y cube divided by x square plus y square. So we need to take y to be equal to 0 here. So that is x cube divided by x square, which is equal to x. So writing here x minus 0 divided by x, which is equal to 1. Similarly, partial derivative of u with respect to y is limit y tending to 0, u0y minus u00 divided by y. And when putting x equal to 0, we are getting, and when putting x equal to 0 on u, we get minus y cube divided by y square, that is equal to minus 1. So this is minus y minus 0 divided by y, which is equal to negative 1. Similarly, we can find that partial derivative of v with respect to x is 1. And partial derivative of v with respect to y at the origin is also coming out to be 1. And what are the Cauchy-Riemann equations? These are the Cauchy-Riemann equations. So at the origin, are these satisfied? Yes. Del u by del x is 1. Del v by del y is 1. Yes. And secondly, del u by del y is negative 1. And del v by del x is 1. That is equal to, because of negative sign, it is minus 1. Yes. So these two are equal. So yes, Cauchy-Riemann equations are satisfied at the origin. Hence, CR equations are satisfied at the origin. And now to show that f dash z does not exist at the origin. So for this, taking limit z tending to 0 on f of z minus f of 0 divided by z. So this is equal to limit z tending to 0. What is f of z? I have to write the complete function over here. Minus f of 0, it is given that f of 0 equal to 0. This is given to us. So writing here 0 divided by z. I'm writing z to be x plus iota y. Because everything is in now x and y, so we have to write here xy tending to 0, 0. For z tending to 0. So writing this again as multiplying this with 1 divided by x plus iota y. Now if I take z tending to 0 along the line y equal to mx, right, where this m is belonging to the set of real numbers, what we get, just replacing y equal to mx in this limit. And now when replacing y equal to mx in this limit, we are getting everything in x, right? So in the limit we have to take x tending to 0 only. So this is equal to, I have to write now x tending to 0 because here it is x cube minus, because y is equal to mx. So y cube becomes m cube x cube plus iota times x cube plus y cube, that is m cube x cube divided by x square plus y square, that is m square x square into 1 divided by this z, that is x plus iota y. So writing here mx. So limit x tending to 0. Taking x cube common from the numerator, we get 1 minus m cube plus iota 1 plus m cube. And if I take x square common from the denominator, I get 1 plus m square, right? So I have taken x cube common from the numerator and x square common from the denominator, and also I can take x common from here. I get x into 1 plus iota m. So x square into x becomes x cube, which is cancelled out with this x cube. So limit x tending to 0 is on 1 minus m cube plus iota times 1 plus m cube divided by 1 plus m square into 1 plus iota m. And this limit is equal to, because there is no x, so it is as it is. Now this value is depending upon the different values of m, right? So here the limit is not unique. It is depending upon m, the different values of m, right? Where m is belonging to the set of real numbers. So hence, limit does not exist at the origin. Therefore, the limit z tending to 0, f of z minus f of 0 divided by z does not exist. Or this is f dash 0, right? So in other words, we write that f dash 0 does not exist at the origin. This is what is needed to be proved. Hence the result. Okay, thank you. Stay blessed.